Hello everyone. In this video, we're going to continue our discussion on geometry by discussing two quote-unquote simple theorems. Now these might be something you've already heard before. The idea that there's 180 degrees in a triangle isn't too foreign to anyone, I believe. Something maybe learned in elementary school for the first time. But we're going to be really diving into the why behind it, the proof, if you will, of why this is a theorem. Why does a triangle have 180 degrees? And a second theorem as well, which is just on a second slide here. Now, a side note before we get, and I don't want this to confuse you, but just an idea why this is a theorem, and another kind of for futuristic math classes, the idea that math is always kind of evolving and changing. I took a class in college called non-Euclidean geometry. First day of class, we walked in, the professor asked, how many degrees are in a triangle? And everyone almost laughed, oh, it's a silly question. We're third or fourth year math majors. Someone raised their hand and went 180, obviously. She said, nope. She held up a basketball, drew a triangle on it. And if you do that on a sphere, it's kind of hard to model, but it ends up coming out like this. Almost think about like a soccer ball, like the little panels on there. If you try to draw a straight line, it ends up coming out like a little curve. And if you add up those angles, those aren't going to add up to 180 degrees. But that's a triangle. It's made up of three straight line segments. And that class gets really confusing and starts to blow your mind a little bit, but very interesting nonetheless. That's just an idea about understanding some of these principles and how they exist in a very limited capacity, even though we don't really see that just yet. I'm giving you guys kind of a preview that, hey, all this stuff is temporary for now. You learn something, and then kind of later on down the line, you learn that maybe that's not always the case. All right. Anyway, before we get too off track, the idea that the triangle sum theorem is the idea that the sum of the three interior, the inside angles in a triangle is always 180 degrees. We just learned that's not always the case, but that's why it's a theorem. And that's in the Euclidean world, like the flat piece of paper triangle. Okay. So if we add up angle 1, angle 2, and angle 3 in my little diagram, we should get 180. Think about like an easy example, an equilateral triangle, 60, 60, 60, right? Every triangle, if we add up the three angles, they're not always necessarily going to be the same, but they always add up to 180. So why is this the case? How can we prove that this is always going to happen other than just blindly kind of accepting it? What I have here is a little sketch. We have a triangle kind of squeezed between two parallel lines. Those little arrows indicate that these lines are parallel. And we're going to go ahead and prove this theorem. Okay, so I just arbitrarily labeled 1, 2, and 3. You can call these anything. That doesn't mean like 1 degree, just like the name of that angle. So I could just say angle 1. I'm also going to add 2 more. We'll add these in a different color because they're not part of the triangle. But I'll add this guy and this guy. Okay. So, and you guys can kind of pick up on some of this already. I don't want to give away the next one just yet. Take a look at this top part. What can we say about angle 4, angle 1, and angle 5? It's maybe a little difficult to see, but together, those three angles, it might be helpful almost if you were looking at this upside down. Those three angles are going to make up a straight line. 4, 1, and 5 make up that one straight line, right? We don't know what they are individually, but we do know that they add up or that they form a straight line together. So we can say that angle 4, angle 1, and angle 5 are supplementary, which means they add up to 180 degrees. So I know that angle 1 plus angle 4 plus angle 5 is equal to 180 degrees. Sometimes you could put like the M in front to represent like the measure. I'm just going to kind of write shorthand here. Okay. Now we can use another idea that we learned. I'm going to erase the highlighting here. Let's change this. The idea, let's get kind of 2 and 3 in the mix here because that doesn't help us so far. Why do we care about 4 and 5? Those aren't inside the triangle. We got 1 in that triangle, angle 1. But let's get 2 and 3 in the mix. Let's start with angle 2. Angle 2 and angle 4 have a special relationship. Does anyone see it? I don't know why I'm asking that, like someone's going to raise their hand. Angle 2 and angle 4 are going to be congruent to one another. How do we know that? Once again, we don't know their measure. I don't know if angle 2 is 50. I can't guarantee that angle 4 is also 50. I see that they're both kind of acute here, it looks like, but how do I know they're congruent to one another? The reasoning would be alternate interior angles are congruent. And that's why the parallel lines were kind of necessary here, because we can dig out these relationships. Without that, one, we're not going to have angle 4 and angle 5, and two, we couldn't use that transversal parallel line ideas that we talked about 2 days ago. So we know angle 4 and angle 2 are congruent from alternate interior angles, right? Kind of treating this as the transversal. They're on alternate sides of the transversal, and they're inside the parallel lines. Okay. Now, in the same token, we can say the same thing about angle 5 and angle 3. Those are also congruent to one another. By the same reasoning. And once again, this is just a different transversal. It would be like this guy. They're on alternate sides of it. They're inside the parallel lines. We know they're congruent to one another. And now all we have to do is kind of like an algebra concept. Think about substitution. I know angle 2 and angle 4 are, for all intents and purposes, the same. So I can replace angle 4 with angle 2. I could swap that out. Let me go ahead and do that. Since I know they were the same measure, I can do that. And same thing with angle 5. I know 5 and 3 are the same, so I can logically replace it or substitute its value. And we've just proved this idea. We've shown that angle 1 plus angle 2 plus angle 3, which are the three interior, basically the three angles that make up the triangle, will add up to 180 degrees. Now, this is very informally done. When we see proofs next year, we're going to be doing like the statement reasons tables that you've probably seen in the past, maybe very briefly. But this is just kind of describing where this proof comes from, all based on alternate interior angles. Okay. Second one. This one might be kind of new if you've never heard this before, and it's not that difficult. One of those where the wording is somewhat more confusing than the actual idea here. So let me just read it out and then I'll break it down a little bit simpler. It's called the exterior angle theorem. First of all, just explaining what an exterior angle is. An exterior angle is outside the particular shape when you extend one side. So, and any shape can have an exterior angle, hexagon. But in this case, a triangle, notice one side, it's like I took my ruler and I just like kept going. Now that outside angle that's formed, see this? That outside angle that's formed is known as an exterior angle. It's outside the shape. Okay, the exterior angle formed when you extend one side of a triangle is equal to the sum of the two non-adjacent angles. So what does non-adjacent mean? Adjacent means kind of like next to or touching. So in this case, if angle D is our exterior angle, it's touching or it's next to angle C. So that's not going to be in play here. The two non-adjacent angles would be A and B. Okay? So those are the angles that aren't touching, aren't right next to angle D. So in other words, what this is saying is A plus B is going to equal D. If this is 30 degrees and this is 50 degrees, this would be 80 degrees. Very simply put, right? That's always going to hold up. Now, you can be given a problem where there's like some algebra here that might say like, oh, angle A is 2x plus 5 degrees, angle B is this. So you have to know this theorem in order to solve it. Obviously, there would be other ways to figure this out if you didn't know the theorem, but they might use algebra almost requiring you to know this theorem. And let's go ahead and prove or show where this one's coming from. Okay. So how we do this is somewhat similar. We're going to use the triangle sum theorem that we just talked about. So what did we just learn? We learned that angle A plus angle B plus angle C, if you add them up, you get 180. Good timing that we just learned that. Now, if we look at angle C and angle D, those form a linear pair. Together, they make up a straight line. So we say those are supplementary. So angle C plus angle D, supplementary, linear pair. That's not the triangle sum, that's the linear pair supplementary definition. Okay? And once again, we're going to use some kind of algebra substitution type stuff here. So think about this of almost like a system of equations might be helpful. If you look at equation 1, the top equation, and equation 2, notice how both have angle C in the mix. So if we were to subtract angle C from both of these, let's go ahead and do that. Almost like removing them, if that makes sense. How do I want to write that? You know what? Let's move it to the other side. Almost like treat it like a variable. But you're going to see very quickly what we're getting at. So what I did was subtract C from both sides in both equations. So now if we notice, we have angle A plus angle B is equal to, don't even worry about what that says on the right-hand side. And notice the second equation has the exact same setup. So I could have just set these equal to one another. That's what I was trying to do as well. So you could set these equal to one another and then subtract out the C. Let's do that. I lost like my process in the middle there, but we'll fix it on the spot. That would have worked as well. It's just more confusing. So I'm going to set these equal to one another because they're both equal to the same thing. Substitution. Two things equal to the same thing are equal to each other, or the transitive property. Okay. So everyone see how I'm allowed to kind of do that? They're both equal to 180, so I can set them equal to one another. And now I can rid the C. Now I can kind of legally subtract whatever C was. It's 50 degrees. You're allowed to subtract it from both sides. And we're left with this, which is the exact same definition we had written up above. Angle A plus angle B is always going to add up to angle D, whatever that particular measure. Remember, all of this notation that we're writing here, we're talking about like the measure of the angle. I really should be writing M everywhere. Like we're talking degrees. Oh, 50 degrees, 60 degrees. So notice how we got that matched. So the proof here has to do with, once again, not using like alternate interior angles, but just the idea of knowing supplementary, knowing the relationship in a triangle itself. So these are pretty simple theorems to prove. The exterior angle theorem might be new to some of you guys. Like I said, maybe jot that down if you haven't seen it before. The outside angle is going to be equal to the sum of the two non-adjacent angles in a triangle. And then obviously the triangle sum theorem, which we talked about first, is always going to add up to 180 degrees, unless you're in a college math class where that doesn't happen to be the case. But anyway, thank you guys for watching. This is probably gonna, for all intents and purposes, gonna conclude our geometry discussion. I wanted to give you guys a very brief preview of things to see coming up in September. The last 2 days, we'll wind down a little bit. We'll do a little bit of like reflection and stuff like that, and have a little bit of fun in the mix as well. But thank you for watching and participating in these, and have a great day.